Thank you very much for the invitation to speak here. It's a great pleasure. And so I'm going to be talking about generalized cusps in projective manifolds. How do I advance the screen? So, thank you. This is an overview. So if you have a three-manifold, for example, you delete a knot from the three-sphere, then maybe it has a hyperbolic structure. So here, for example, if you delete the figure 8 knot from the three-sphere, a knot complement has a complete hyperbolic metric on it, in fact, a unique one. And this manifold's not compact. The end is topologically the product of a torus and a half-open interval. And it's got a hyperbolic metric on it. And you can truncate the end by cutting it along a torus. And this torus, well, you might choose a torus here or further out. So there's a family of tori you can choose to truncate the end along. And the metric decreases exponentially as you go out. And on the boundary of this cusp, you have a Euclidean metric on a torus, but it's only defined up to scaling. So you have a Euclidean metric defined up to scaling. You can think of this, then the boundary as a quotient of the complex plane by a lattice of the form z direct sum integer multiples of some complex number with imaginary part 0. So the geometry in this cusp is determined by a complex number with positive imaginary part. It's the shape of the cusp. So the summary is that cusps in hyperbolic manifolds are parameterized by a complex number with positive imaginary part. I want to extend this picture to not just hyperbolic manifolds, but properly convex manifolds. And one discovers what I'll be explaining then is that the geometry in the cusp is again determined by a geometric structure on a torus. And the geometric structure on the torus is more complicated. In 2 dimensions, the geometry is, well, first of all, you have a similarity structure, that is a Euclidean torus defined up to scaling. So again, you have this complex number W. But in addition, you have 3 vectors in the plane, well, 3 vectors actually in this parallelogram, A1, A2, A3. And these vectors are not arbitrary. They satisfy the condition that if you take in a product of 2 distinct vectors, you always get the same number, and it's a number that's less than or equal to 0. So it's possible that one or more of these vectors is 0, in which case this constant is 0. The number of vectors for which the number of non-zero vectors is called the type of the cusp. So the type is an integer 0, 1, 2, or 3. And so type 0, when all these vectors are 0, this cusp in a projective 3-manifold is actually equivalent to a cusp in a hyperbolic manifold. At the other extreme, when all 3 numbers are non-zero, then the holonomy of this cusp is diagonalizable. And in between types 1 and types 2 kind of interpolate. So what I'm going to do is actually describe this picture in all dimensions. So here I'm just talking about dimension 3. So one goal is to classify what we call generalized cusps. So that's this kind of structure in all dimensions. And then the next goal is to describe the moduli space of generalized cusps. And so on the face of it, at least, well, in dimension 3, there are 3 different families But it turns out that they all fit together in a very beautiful way to make a connected moduli space. So I want to describe that. And finally, the deformation theory of properly convex manifolds when all the ends are of this type. So that's the goal for these lectures. Now, these lectures are based on a series of papers produced in the last 10 years or so with various people that total something more than 200 pages. So I'm not going to cover all the details. Some of them have appeared and some are on the archive. And at points in the lectures, I'll make reference to these papers. Okay, so by the way, if you have a question, please ask. If there are no questions, then the lecture is a failure. So going to be talking about a real projective space. So R to the n plus 1, real vector space, and I'm often going to call that V. And then we're going to projectivize it. So we take the non-zero vectors and identify two vectors if one is a scalar multiple of the other. And that gives the projectivization of the vector space V. More generally, if we have a subset of non-zero vectors, the projectivization of that subset is the image of X in the projective vector space. So, okay, so the notation real RPN, real projective space of dimension n, comes from projectivizing a space, real vector space of dimension n plus 1. And so I'll sometimes call that RPN and sometimes call it the projectivization of V. The group of projective transformations, linear maps, act on a vector space. They send one-dimensional spaces to themselves. So they send points in projective space to points in projective space. And the center acts trivially. So the projective general linear group acts effectively on real projective space. And so we have a geometry in the sense of Klein, the projective transformations acting on projective space. So this leads to the notion of a projective manifold. So a manifold is something covered by charts with overlap maps. And it's a projective manifold if the charts take values in projective space and the transition maps going between two charts are projective transformations. So all two-dimensional manifolds have a real projective structure. That leads to the question, what about three manifolds? Which three manifolds emit real projective structures? And this is not known. Every non-compact three manifold has a real projective structure for the simple reason that it immerses in Euclidean three space. Therefore, it immerses in projective three space, and that gives a projective structure. With compact manifolds, we know exactly one connected three manifold that has no real projective structure, the connect sum of two copies of real projective three space. And after 10 years, this is the only known example. So here's a question I certainly don't know the answer to. If you have the connect sum of two projective three manifolds, if you have the connect sum of two three manifolds and the result is real projective, is one or other of the manifolds the three sphere? Is it the case that non-trivial connect sums in dimension 3 are never real projective? I don't know. So now I'm going to specialize to convex projective manifolds. So these are special kind of projective manifold. They're the quotient of a domain omega in real projective space by group gamma of projective transformations that preserve omega. And so this subset omega is a convex set. Any 2 points in omega can be joined by a segment of a projective line in omega. And it's actually going to be, well, if I remove a hyperplane from projective space, what I get left is an affine patch. I can identify it with Euclidean space. And so if I take a convex open set in Euclidean space that's bounded, that means that omega is called a properly convex set. And in addition to being bounded, there is no line segment in the boundary of omega, then it's strictly convex. So there is two kinds of convex that we'll focus on, properly convex and strictly convex. And I'll use a notation. Whenever you have a subset of projective space, PGL of that subset means projective transformations preserving that subset. So we're going to be looking at manifolds which are the quotient of either a properly convex domain or a strictly convex domain by an action of the fundamental group M. So we're going to have some isomorphism taking the fundamental group of M into a discrete group gamma of projective automorphisms that preserve omega. And so that's the kind of objects I'm going to be looking at. So a basic example of all this is a hyperbolic manifold. So if we take, for the domain omega, the set of vectors of length less than 1 in Euclidean space, the round disk in Euclidean space, if that's omega, then the projective automorphisms of that domain, you can identify them with isometries of hyperbolic n space, PON1. And I'm going to talk a bit more about that in a moment. In general, projective transformations don't preserve any metric, but when you have a properly convex domain omega, there is a metric on the interior called the Hilbert metric. And it's defined as follows. If you take 2 points in the interior, there's some line segment in omega whose endpoints are on the boundary of omega. And the formula for the distance between these points is given by something involving the cross ratio. The factor of a half here you may put in or not. If you put in the factor of a half, then it has the advantage that when you apply this formula to this disk, you get the hyperbolic metric. If you leave this out, you get a multiple of the hyperbolic metric. In general, this metric isn't a Riemannian metric. It's given by a norm on the tangent space rather than a quadratic form, so it's a Finsler metric. It's a complete metric. Cauchy sequences converge. And because projective transformations preserve cross ratio, it's preserved by PGL omega. Does anybody have a question? So the basic example of this is hyperbolic space. So hyperbolic space, hopefully you've seen it. If you haven't, hyperbolic space, it's a Riemannian metric on the upper half space of Euclidean space. So here's Euclidean space in dimension n. I take the subset where the nth coordinate's positive, the upper half space. And then the hyperbolic metric is a multiple of the Euclidean metric. You divide the Euclidean metric by the height above by the xn coordinate, the height above the, if you like, the horizontal plane. And so that's a Riemannian manifold. If you do this in dimension 2, so you're taking the upper half plane, the group of isometries of orientation preserving isometries of the upper half plane, the hyperbolic plane, you can identify with PSL2R. Now we're going to be interested in cusps, and that means we're going to be interested in horoballs. So a horoball, what is a horoball? If you take a point in hyperbolic space, you can take the ball of radius r around that point. If you move the point off to infinity and increase the radius at the right rate, then the limit is a horoball. It's, if you like, a ball of infinite radius. If I take a point on the xn axis and move it upwards and increase the radius at the right rate, then what I end up with is, as a horoball, is a set of points whose nth coordinate is bigger than or equal to some positive constant c. So take a horizontal plane, hyperplane, all the points above it would be a horoball. And then this metric restricted to the horoball, xn is constant. So the metric restricted to the horoball is actually a Euclidean metric, the induced Riemannian metric. The boundary of the horoball is called a horosphere. Slightly misleading because it's not a sphere, it's actually a plane. It's a sphere with a point removed. And if I take a discrete group of isometries that preserve this horoball, Well, that means that they're acting by isometries on this Euclidean plane. And so if I quotient out a horoball by a discrete group of isometries preserving it, the boundary is going to be the quotient of the Euclidean plane by a discrete group of Euclidean isometries. And the quotient, well, I've kind of indicated here, you kind of have the boundary as some Euclidean manifold, and then topologically you have a product, but metrically the cross sections shrink exponentially. Now, in the picture, this cusp boundary is compact, but in general, the boundary of the cusp need not be compact. So when we're talking in the generalizing these ideas to the properly convex case, we'll be considering both compact or boundaries with generalized cusps with compact boundary and those with non-compact boundary. Now, that's hyperbolic space explained from the point of view of Riemannian geometry. Explained from the point of view of projective geometry, you take Euclidean space of one dimension bigger, and inside of that Euclidean space of one dimension bigger, there's a hyperboloid given by where this quadratic form of signature n1 is -1. And that's this hyperboloid. And then the group of projective, the image of this hyperboloid under projectivization is this disk D in projective space. And the group of linear maps that preserve this quadratic form, that's ON1. If I take the identity component of that, that preserves this hyperboloid, and that's the identity component of the group of isometries of the hyperbolic plane. It preserves H. This acts on the Klein model of hyperbolic space. So here's a picture. The double cover of projective space is the sphere, and here I've just drawn the image of this, a lift of this Klein model of projective space to the sphere. So it's an n-dimensional disk sitting in this n-dimensional sphere, the double cover. There's another model of hyperbolic space in projective space called the hyperboloid model. So in projective geometry, all conics are the same. So a disk is the same as, a circle is the same as a hyperbola is the same as a parabola. And so this was the hyperbolic model, the hyperboloid model of hyperbolic geometry. There's correspondingly a parabolic model where the hyperbolic plane is a set of points lying above a parabola. And that will be important when we're talking about generalized cusps. So I'll talk more about that later. Does anybody have a question? Oh dear, 18 minutes in and we're a failure. Okay, well, in somewhat, so strictly convex projective manifolds, I think of them as a generalization of hyperbolic manifolds. They have negative curvature. When you go to properly convex, you're talking about a domain that can have line segments in the boundary. And an extreme example of that is when the domain is the interior of an open simplex. And the geometry, the geometry from the projective point of view of an open simplex is very different. So I'm going to describe the Hilbert metric on the interior of an open simplex. So we can think of an open simplex projectively if I take the set of points in Euclidean space dimension n+1, where all the coordinates are positive, and projectivize that, then what I get is equivalent to the interior of a simplex in projective space. And of course, the diagonal matrices, if I take a basis of projective space given by the vertices of this simplex, then the diagonal matrices, the positive diagonal matrices preserve this simplex. So the positive diagonal subgroup is a subgroup of the projective general linear group of this simplex. And now if I take the Lie algebra of this, so I can think of the Lie algebra as all diagonal matrices up to adding a multiple of the identity matrix. because we projectivized. Well, then I can identify this Lie algebra with the interior of the simplex. And the way you do that is I use the orbit maps. If I take a point in the interior of the simplex, then the orbit map sends an element in this group D to a point in the simplex by taking the image of the point P under the projective transformation. And using the exponential map, that gives a map from the Lie algebra into the interior of the simplex. So I can identify this Lie algebra with the simplex, basically by taking the exponentials of the coordinates in the Lie algebra. Then the fact is that the Hilbert metric on the simplex corresponds to a norm on this vector space. And this norm is a very nice, pleasant norm. The norm, so here's a norm on, well, this vector space is a real vector space of dimension n-1. So take some diagonal matrix up to adding a multiple of the identity matrix, that's some matrix T. And if I exponentiate T, I get a point in this group. The norm of this, which is the same as the distance of the base point in the simplex from its image under the exponential of T, the norm we're talking about, is called the hex norm. And what it is it's the supremum of the difference between the I and j coordinates of this. So you can see that this formula, if I add on a multiple of the identity matrix, this formula doesn't change. And the proof is very simple, actually. I mean, if you think, if you take 2 points in a simplex and you calculate the Hilbert metric, what you're going to do, you're going to take a line segment that goes, a segment of a projective line that goes through those 2 points. And the endpoints of that segment are on faces of this simplex. And those 2 faces correspond to 2 coordinates, I and j. And so if we take a linear projection of this vector space to the vector space dimension 2 and restrict to the positive quadrant, we've got a map from that gives a map from the projectivizer from this n simplex to the 1 simplex. And the Hilbert metric in the 1 simplex is given by this formula. And so that's why that's the formula for the Hilbert metric on a simplex. So from that, you can understand what the unit ball of this metric is. So to understand what the unit ball is, think about taking the vector in Euclidean space dimension 1 where all the coordinates are 1. And take the orthogonal complement of that. So the hyperplane in Euclidean n+1 space orthogonal to this, that's V perp. Then if you do orthogonal projection of this vector space onto V perp, and you take the unit cube in here and project it orthogonally into this hyperplane, that is the unit ball of this norm. So for example, if you do this in dimension 3, well, if a 2 simplex comes from projectivizing dimension 3, you're projecting a cube along the main diagonal to the orthogonal plane. The image is a regular hexagon. And that's why this metric, I call it the hex metric. If you do this in 1 dimension higher, you're taking the image of a 4 cube, doing the corresponding orthogonal projection, you get a rhombic dodecahedron. So the thing about these metrics are that the unit ball is not strictly convex. And this leads to the fact that if you take a curve in the hex plane, that you'd have non-unique geodesics. If you have a curve in the plane, so the tangent vector to the curve is always pointing into the same face of the unit ball, then it's length minimizing. So there are lots of length minimizing paths between 2 points. So it's very unlike negative sectional curvature. Summary, properly convex geometry involves well, I think of it as, well, it involves different phenomena. It involves negative curvature, and it also involves this very kind of degenerate kind of geometry. Are there any questions? Okay, so the next thing we want to do is get some understanding of isometries of a domain. So this material is an expansion of the discussion here. So we have a properly convex domain omega, and we have some projective transformation that preserves omega. Then it has something called the translation length. The translation length is the infimum of distances that a point is moved by the transformation. So there's a basic fact that the translation length of a projected transformation, you take the eigenvalues of largest and smallest modulus in A. Now, A is only defined up to scalar multiples. You take the ratio of those eigenvalues, so that's unchanged by taking scalar multiples, and then you take the logarithm of the absolute value. That is the translation length of an isometry. And it's actually quite difficult to prove that. In fact, I'll be doing that. The isometry is called hyperbolic if the translation length is positive. It's called elliptic if there's a point in the interior of omega that's fixed. And in that case, A is conjugate actually into the orthogonal group. And in the remaining case, it's called parabolic. So there's a way you can picture. So elliptics, we understand, they're just rotations. What about hyperbolics and parabolics? Well, hyperbolics and parabolics permute a pencil of hyperplane. So here I've got a domain omega. Here I've got a projective hyperplane of codimension 2 called C. And then I'm taking all the hyperplanes of codimension 1, projective hyperplanes that contain C. So that's called a pencil of hyperplanes. So for every point in the RP1, there's some hyperplane going through the core. And then the hyperplanes in this pencil that meet the domain omega, well, there's an interval's worth of them. And the deal is that if you have a hyperbolic, it's a fact that there is some core, there's some codimension 2 hyperplane that's preserved by the hyperbolic. And the hyperbolic, there's a hyperplane that's tangent to the domain omega at one point, or maybe more than one point. It might be bigger than one point. This doesn't have to be strictly convex. You get these two hyperplanes, they're fixed. And the action, well, what this map does is it sends hyperplanes to hyperplanes. So this hyperbolic is moving away from the repelling fixed point towards the attracting fixed point, and it's moving hyperplanes. And in fact, there's some axis that's preserved. One catches that in the cases, the way I've drawn here a strictly convex domain, and in that case, there's a line, projective line segment that's mapped to itself, translated along there. In the properly convex case, it's possible that this axis is actually at infinity. So you have this picture of the hyperplanes being moved, but this axis might actually be infinity. The parabolic case is a kind of limit where this core of the pencil has moved in and touches the boundary of the domain at maybe one point or maybe more than one point. But there's still this pencil of hyperplanes that are moved by the parabolic. So that's a kind of geometric picture of what the possible maps are doing. Any questions? So in order to prove this fact about translation length, one needs to think about elementary subgroups. So if you have a domain omega, a subgroup of projective transformations that preserves omega is called elementary if there's some point P that's fixed by the entire group. and so P might, that you can't see it, that's actually in the closure of omega. So the point P might be in the interior of omega, it could be in the boundary of omega. So group's elementary if there's a common fixed point either in the interior of omega or the boundary of omega. It's called doubly elementary if there's a fixed point in the boundary of omega and there's a supporting hyperplane. So here H is this hyperplane. So, and the hyperplane is also fixed. Oh, that should be G. Oh, sorry, no, okay, that G should be gamma. G and gamma are the same thing. So a group is elementary if it fixes a point. It's doubly elementary if the point's in the boundary and it also fixes a supporting hyperplane. Another way to think about this, a supporting hyperplane corresponds to a point in the dual projective space. And so doubly elementary means you fix a point in the boundary of the domain and you fix a dual point in the boundary of the dual domain. So it's kind of doubly elementary. Okay, so so a couple of propositions. If you have well, this is nothing to do with projective geometry. If you have a subgroup of general linear group over the complex numbers, if it's irreducible and there's a uniform bound on the traces of every element in G, then in fact, there's a uniform bound on all the entries in all the matrices. And this is a simple consequence of a theorem of Burnside. It follows from that if you have a bounded subgroup, so if you have a subgroup of projective transformations that preserve omega, and here I'm assuming we've lifted to the special linear group, all these matrices have determinant plus or minus 1. Then there's a common fixed point for this group, and that point is either it's in the closure of omega. And the proof is the following. I mean, if you take a point in omega, well, you can orbit that point by the closure of this group. The closure of the group is going to be bounded as well. And if you take the convex hull of that, you'll get a compact, properly convex set in the interior of omega, which is preserved by G. Now, Zorn's lemma tells you there's a minimal such set, and that minimal such set's only got one point in it because otherwise you could do this to it. And so that. Okay, so those are lemmas we want for this. So this is, we have a group that preserves some properly convex domain. It's a discrete group, and every eigenvalue in this group of matrices, the absolute value, they may be complex, but they've all got absolute value of 1. Sorry?
When you say G is bounded in the first bit.
What your question? What does bounded mean?
That's n by n matrices.
Oh, what does it mean to be bounded in n by n matrices? Yeah, well, this is a vector space. This is a bounded set in it. In other words, all the matrix entries and all the group elements are less than a fixed constant in norm, modulus, absolute value. Okay. Okay, so we have a group and a discrete group, and every eigenvalue and every element has modulus 1, then the group is doubly elementary. And so, well, the first case is the group is irreducible. And I'm cheating a little bit here. There's a difference between irreducible over the complex numbers and irreducible over the reals, and the details are in the paper. But if the group's irreducible over the complex numbers, then this first lemma tells us that there is a fixed point. And the fixed point might be in the interior, it might be in the boundary. On the other hand, it's got to actually be in the boundary because the group is infinite and discrete. And if it was fixing a point in the interior, it couldn't be infinite and discrete. So there's actually a fixed point in the boundary. Now, So take that fixed point in the boundary and think about all the supporting hyperplanes at that point. So if it's strict, there might be a unique supporting hyperplane. And then, of course, that hyperplane will be mapped to itself. In general, the set of hyperplanes isn't unique, but the set of hyperplanes is actually a compact convex set in a projective space of one dimension lower. The set of hyperplanes is a properly convex set that's compact and one dimension lower. And so this lemma then tells you that the action of the group on this set of hyperplanes has a fixed point. And so that gives you the invariant hyperplane. Yeah, supporting hyperplane containing P, yeah. So this is a supporting hyperplane at E, yeah. So the other possibility then, if G is reducible, so there's some decomposition of Euclidean space into two subspaces A and B, and this subspace A is preserved by the group. So what happens in that case? Well, if you think about projectivizing this subspace, you get some projective subspace of smaller dimension. One possibility is that this subspace of smaller dimension intersects omega bar. And in that case, induction on dimension gives you the result. The next possibility is that the dimension of B is 1. Now, the dimension of B is 1, then A, when you projectivize it, is a hyperplane. That means this group is preserving a hyperplane. And it means if you have a group preserving a hyperplane, it's an affine group. And an affine group preserves centroids. So if the dimension of B was 1, the centroid of omega would be preserved, but the centroid's in the interior of omega, and that's a contradiction, so that can't happen. So that means that B's got dimension 2 or more. So now there's a map, a projection map. If you take Rn and remove the set of points where the B coordinate is 0, you get a projection from projective space with this projective subspace removed to the projectivization of B. And we can look at the image of omega under this projection. And because omega is convex, the image is going to be convex in here. Now, the fact the dimension of B is at least 2 actually means this set is properly convex. And the reason is that because B's got dimension 2, there's a projective hyperplane, codimension 1, that contains the projectivization of A strictly. And that hyperplane doesn't meet the closure of omega. So when you take this image under the projective, when you take the image under pi of H, you get a codimension 1 projective space that's disjoint from the image of omega. And so that should be a prime there. It should be, sorry, no, okay, that's fine. So that means that omega prime is actually properly convex. So in this situation, then, again, we can apply induction, and we now know there's a point in here that's fixed by this group. And then if you look at the preimage of that point in here, you get a projective space of smaller dimension that definitely intersects the closure of omega. And so this is a space of low dimension. Again, by induction, there's a fixed point. And every time I prove there's a fixed point, this argument here actually tells you that there's also a fixed hyperplane. So, so this leads to the following result, which is if you have so again, you have a properly convex domain, and we have some finite set of projective transformations preserving omega, and all the eigenvalues are 1. So think parabolics. We've got a finite set of elements where all the eigenvalues are actually 1. In that case, there is a point in omega that is moved less than epsilon by every element in this finite set. In particular, if you have a single projective transformation and all the eigenvalues are on the unit circle, then in fact, the translation length of that element is 0. So this theorem is actually what proves this formula for the translation length. So this result. So this result kind of illustrates the kind of geometrical reasoning one does in analyzing parabolics and properly convex sets. Okay, so we've got this finite set of elements, all the eigenvalues are on the unit circle. So that means all these elements have bounded trace. So by the previous result, that means that this set of elements fixes some point in the closure of omega. And if the point is actually in the interior of omega, then we're done. I mean, the interior, if it's a point in the interior of omega, that point is moved distance 0, we're done. So we can assume this point's in the boundary of omega. So now we're going to look at, now this is where I want to use my iPad. Now we're going to look at the space of directions. So we've got a point in the boundary of omega that's fixed by this set of elements. And we're going to think about all the hyperplanes. We're going to think about the space of directions at omega. So what's that? Think about all the lines going through the point P that contain a point in omega. That's the space of directions of omega. It's a subset of a projective space of one dimension lower. And because omega is convex, the space of directions is a convex set. And it's actually so that convex set is some properly convex set times an affine space. If this set omega had a unique supporting hyperplane, then the space of directions at that point would be an affine space. This would be a single point. If P was a vertex of a simplex, then the space of directions would be a simplex of one lower dimension. And in that case, this would be a simplex of one lower dimension, and that would be a single point. In general, the space of directions is a product of some properly convex set of smaller dimension and an affine space. If this is a single point, if the space of directions is an affine space, that actually means that the point P has a unique supporting hyperplane there. And in that case, the result is obvious because if you think about how the Hilbert metric works, because of a unique supporting hyperplane, if you take a point very close to that point P, the shape of the boundary, it's almost flat there. When you think about how the Hilbert metric works, it means that any point close to P is going to be moved a very small distance. So when this is a single point, the result is obvious. So again, we're going to kind of do proof by induction on dimension. So we've got this group acting on omega. This group acts on the space of directions. So it acts on this space. And so it acts on omega prime. And the action of this group on omega prime has the property that all the eigenvalues are on the unit circle. So that means then there's a fixed point in the closure of this set. So there are various possibilities. One point is that this fixed point is actually in the interior of this set. And if the point's in the interior of this set, it means that if you take the preimage of this point under the space of directions intersect omega, that's actually a properly convex set. It's invariant under S, and induction on dimension gives you the result. The interesting case is actually when this point is in the boundary of this set. And this is where the kind of the complexity comes in, if you like. So we've got the original set omega. We've got this finite set S of transformations preserving some point. And here I'm indicating some lines coming out of this point P. There's a projective transformation. Well, we're taking the space of direction. So each one of these lines maps to a single point in a projective space of 1 dimension lower. The image of omega under this map, the space of directions, is this set here. It's the product of omega and an affine space, if you like, coming out of the picture. There's a fixed point Q in the boundary of omega prime for this group action. By induction on dimension, there's a point X prime in this domain omega that's moved a small distance by each one of these group elements. So I'd like to deduce from that that if I take 2 points that map to this pair of points, they are moved a small distance in this domain. So to do that, I take a segment in this domain with endpoints A prime and B prime. And instead of measuring the distance between X prime and its image in omega, I measure it in this segment. So this segment is called L prime. And so the distance, because the segment is smaller, the distance in L prime between this pair of points is bigger than the distance in the domain. And I can choose these points big enough, close enough to the boundary, that this is still less than epsilon. Now then, if I move X and S, and therefore S of X, closer to P, eventually there'll be a pair of points A and B in this domain that map to this pair of points. And so by taking these points close enough, I'll have a segment here that maps to a segment there. And then the distance between X and S of X in this segment is the distance between their images in this segment. And the distance here between this pair of points is less than the distance between this pair of points in the domain, and we're done. So, sorry? 2 minutes left, right. That might be a good place to end in that case.